I'm going to talk about what I did during my master thesis, and the title was Asymmetric Heat Transport. So, a device has asymmetric heat transport. I'm going to place here. When there is like a dependence of its properties with the spatial configuration of the environment. That is, for example, when we place, this is the device with the asymmetric heat transport, also called heat rectifier. And when we place the hot bath in one side of this device, we can see that the thermal current, that is this red arrow, is big. But when we exchange the bath and we place the hot bath where was the cold bath, we see that the thermal current now is smaller. So this device is acting when we have one spatial configuration of the environment as a conductor, and when we change it as an insulator. Yes. Well, I am saying that it's different.
Oh, you're preparing a device in which the coupling is different when you switch.
Yes, yes. In fact, yes. What we are saying is that yes, this bath, yes, the coupling between this place is different than this one.
But the baths are equal.
Sorry?
The baths are the same.
Not at all. I am going to say what's the difference. But yes. So this is a heat rectifier, and it's just the thermal analog to an electrical diode. And okay, these devices are going to be important in small electronics or quantum technologies, since we need to control the temperature of a small system. Like, for example, in quantum technologies, we need to keep one system at very low temperature to have quantum properties, but at the same time, we need to allow this system to dissipate the energy. And these kind of devices are very useful to do so, because at the same time, we also isolate the device, the quantum device, or the interesting device from possible thermal fluctuations of the environment. But yes, we need these heat rectifiers to be macroscopic or quite big.
I know you're getting into it, but do you need work to reduce to make it asymmetric?
If I need, sorry?
Work. Do you need to spend work to make?
No. I mean,
you're just considering like two ideal separate situations, right?
Yes. Sorry, can you repeat the question?
It's a process that you transform the alpha diagram into the one.
We have one device. We construct a device, and all what we do to it is just to exchange the baths. We do not apply work during one. I don't know if I am answering the question.
So this heat rectifier is directional. I mean, okay, if it flows from left to right, it permeates the whole flow, and if the direction is changed, is it something?
Yes, can you repeat?
The heat rectifier, what you were saying, I mean, the path from hot to cold, right? Heat is moving from hot to cold, then from left to right, then the flow is more.
Yes.
If somehow it's direction, it's like a diagram.
Yes, exactly that. This is the heat rectifier, and this is how it acts under one configuration of the environment, of the path.
Yeah, but then I don't like understood like expression. Because like the thing is like there is a relation between heat and work. That's what he's mentioning.
Okay.
Because you need to perform some work on the upper diagram, so you transform it into the second one.
No.
Exchanging the result.
Yes.
Because bias.
Okay, so my question is, both processes are obviously spontaneous. From hot to cold, that's fine. But the heat rectifier, since it makes the direction of flow heat faster from left to right. Compared
Yes,
to right
okay.
to left. Does that device need an external power source? Or
Yes, the external power source are the bats. In fact, these bats are like performing work over this system. And for example, this hot bat is performing work in this part of the system, and then there is like a current to the other side.
okay.
Something like okay. Okay, but since we need like macroscopic devices, macroscopic heat rectifiers, it usually be formed by a lot of subsystems. So to design and then compute analytically the dynamics of this large amount of subsystem is almost impossible. So what was done is to use like some folk theorems that say, for example, that we need asymmetry when we are designing this device. We need some kind of asymmetry from the point of view of heat current. And another folk theorem that is very popular is to say that when we have two systems that are in contact. Yes. Yes. When we have two systems that are in contact, and the frequency of the dynamics oscillation of one system is much bigger than the other one, then we can say that the dynamics of one system is not affecting the other, and these two systems are not going to behave as a conductor. They are going to behave as an insulator. But when we have two systems with similar oscillation frequencies, then it can behave as a conductor. So we would like to check this popular folk theorem, and to do so we are going to focus on this very simple model that was introduced in this paper and consists in two ions with different masses. Each one is trapped in a different harmonic harmonic trap, with constant KL and KR, and each one in a different bath, and the baths are modeled as Langevin baths. So we only need two coefficients to characterize the bath, and it's the temperature and the dissipation coefficient. And finally, both ions are coupled by a harmonic potential with constant K. We are going to treat the whole system classically because the system can be treated using quantum mechanics, but it's more complicated and it does not give any advantage, any relevant information. So the main advantage of this model, although it is not realistic, is that everything can be computed analytically. And the rectification is, yes, the rectification is usually defined as the absolute value of the flux, of the thermal flux when we have one bath configuration. For example, we place the hot bath in the right place minus the absolute value of the heat flux when we have the other configuration, divided by the maximum value of the heat flux. So the rectification is bounded by 0 and 1, and 1 is the ideal rectification. So if we define the rectification in this way, a parametric exploration over the parameters of our model can be done, and here we can see the rectification for different values of KR, and KL. And we can see that the maximum value of the rectification follows almost this straight line. And in fact, in the weak dissipation regime that is given by these conditions, like our chain, our two ions are not very coupled to the path, this straight line is given by this condition. These conditions is like we ask for the frequencies of both ions to be similar, and over this line the rectification is given by the masses ratio and the dissipation of the path ratio, and that makes sense since when we have more asymmetry, these ratios are going to be big and we are going to have more rectification. So if we, okay, but we cannot, we have physical limitations to make these ratios as large as we want.
Sorry. Is there a physical meaning behind this equation?
Sorry?
Is there a physical meaning behind this equation?
Behind this one or this one? I think it's like asking, if we suppose we have two harmonic oscillators, each ion is a harmonic oscillator, I think this equation is like asking to have same frequencies, same eigenfrequencies.
So they have the same frequency. Yeah.
Yes. So if we make both, okay, just to see, if we make both ratios equal and equal to a value c, we can see that increasing both will reach the maximum value of the rectification. And I want to point here that for c equal 1, we have 0 rectification since there is no asymmetry. And for example, for c equal 10, we have like 0.8 rectification. That is a large value. So at the start of the presentation, I said that we want to relate like how similar were the oscillation frequencies of two systems, and to do so, we are going to introduce the spectral density. Since we are using bands, they are going to include in the dynamics random forces, so that the velocity and the positions are random variables, and these angles means average. So we are defining the spectral density for the E ion as the average of the Fourier transform of the velocity of the E ion multiplied by the complex conjugate of this number. Average over position and velocity are going to be random variables because the bands have random forces. So average over these random variables. So here we plot the spectral density of both ions. In the here the black line is the left ion, and the blue line is the right ion. So when we have the C equal 1, that is when we have masses ratio equal 1 and dissipation ratio equal 1, we see that the spectral densities are like are very similar. There is like a big overlapping, a large overlapping. When we have the forward bath configuration, that is, for example, when we have the hot bath in the left side. When we exchange the bath, and now we place the hot bath in the right side, we see the same, is this figure, and we see the same overlapping of the spectral densities. So if we use this fourth theorem, we would say like we are going to have we have a conductor, and when we exchange the bath, we also have a conductor. So there is no rectification.
Javi, what do you want to learn out of this process of doing this?
The main goal could be to use like if we want to design a heat rectifier, the natural question is try to maximize the thermal current in one direction when we have one bath configuration, and minimize the thermal current in the other direction when we have the other bath configuration. But this could be really complicated because to compute the thermal currents sometimes is complicated.
So in the end, you want to
So
kind of define or learn the couplings that does it, that maximize in one direction and minimize in the other.
yes. Can you repeat the first part?
I mean, you're speaking about these couplings you have in your systems
Yes.
that can maximize these heat when you have this first situation, but you also want to know the couplings that like minimize the other way around.
Yes.
When you do this transformation.
Yes. Yes.
Cold and hot.
Yes. But
reservoir.
yes.
And that's the goal of the thing.
Yes.
You want to learn these parameters, these couplings.
It's not like this at all. What I want to do is just to be able to. This is. I am not focusing on only this model, but a bigger ones. So what I want to say is translate the problem from looking to the thermal current to looking to the spectral densities, because maybe it's more simple.
Yeah, but what is the problem you're trying to solve?
I want to say how spectral densities are related with thermal current.
Okay.
Or something like that.
Spectral densities and thermal current are related in a similar way to like electrical current and the energy bands and the Fermi level or something like that.
I don't know.
Because I don't know how to really, I don't really see the relation between the spectral density and the thermal current.
Yes. Okay, I am going to show the relation in the next slides, but yes, it's not trivial at all, at least for me, that there is a relation. So if we now look at this C equal 10 case, we know that in this case we have like a rectification of 0.8, and in these figures we can see that we have like in one case some overlapping of the spectral density. So using this Folk theorem we can say that it is behaving as a conductor, but when we exchange the baths, the system is going to behave as a insulator. So using this Folk theorem we also can say that it is going to be a heat rectifier. So it makes sense that this Folk theorem is true. But we're going to try to compute the exact relation between spectral densities and thermal flux. So for our system, we can just define the thermal current in this way. That is just the work that is doing one ion over the other, and then we Fourier transform this expression, and we end up with this. And after some calculations, we can say that the thermal current is bounded by this quantity. And we can call this quantity like the overlapping of the frequencies of both ions, since we have an integral over the frequencies of a function of the product. So like this expression, this quantity is giving us how much the spectral density of both ions are are similar or dissimilar. Okay, but this is not the relation we would like to obtain. In fact, we would like to have like a proportionality between the matching and the spectral density, and that's what it was supposed in the literature. So here we plot the flux and the spectral matching for different values of C, that is for different values of the parameters of our model. And we can see that, yes, as it was expected, the matching is bigger than the flux, but what I want to point here is that they are very similar. Like they have the same, yes, both are decreasing and the same shape. So what we would like to say is, okay, now we are not going to look at the thermal current, we are going to look to the matching. And to design a heat rectifier, we are going to say we need a device that goes from matching to no matching. Maybe this is easier to do that. So now we need to explain these figures that are the ones that produce the matching. And to do so, we know that when a system have normal modes, the dynamics are a superposition of normal modes. So the spectral densities are going to be delta functions. But in our system, we cannot do that. So we are going to approximate this two-ion chain by a two-ion chain that is not affected by random forces, but have some dissipation. And now this system is going to be like this system can be described by normal modes, and the natural frequencies are going to be given by the poles of the dynamical matrix A. So here I have plotted the poles of this dynamical matrix for different values of C. It's the same figure as this one. And what I want to say here is that it's in the real axis is in this axis, in the y1, and the imaginary axis is in this axis. Since we have dissipation, the eigenvalues of A are going to be complex because we have some oscillation, but at the same time, the modes are going to decay. In this figure, we only see like positive frequencies, so we have to look to this place, and each pair of two modes, two eigenfrequencies, are going to produce the peaks. Okay, and now here these two and these two like are closer, so these two peak. Oh no, this is not a good example. Here, these two and these two are closer, so the peaks are going to be closer. And the real part, for example, if we look to this pair, the real part that is associated with the dissipation of the mode give us the width of the peak. That's why here we expect a peak here. In fact, we see here two peaks, and here only one peak. The peak we are not seeing is because it's very weak. But maybe we are not so interested in the position of the peaks, but how or why both ions behave so different when we are at a natural frequency, or yes, eigenfrequency. And this is given by the ratio between, for example, yes, the ratio of both spectral density near, for example, the end peak, yes, near the end peak is given by the ratio of the oscillations of both ions when only this mode is excited. And that's everything I wanted to say.
Okay.
Yes.
Question before this. Are you close to equilibrium?
Sorry?
Are you close to equilibrium?
No. No, no.
Far from equilibrium.
No, sorry. I am in the equilibrium.
Close to equilibrium, stationary equilibrium.
Yes, yes.
So can this be viewed as the first order fluctuation relation? This looks like very much a fluctuation dissipation unit, like cool.
Okay, I didn't know.
Yeah, it's I mean, it looks very like this.
Okay.
One of the forms of these units. In first order, because you're considering weak company.
Yes.
And closure, yeah, this should be interpreted as a sort of fluctuation unit. In the same spirit of Ubuntu,
Okay.
like specific X is a fluctuation.
Okay. Okay. And that's everything I wanted to say. The model was introduced in this paper, and that's all. If you have any question.
It looks precisely with these groups as well. If you identify.
Yeah,
So you can like you don't have exponential behavior on these.
oh, because it's very close to equilibrium, so it's supposed to be the data balance.
Yeah.
Because in the stationary equilibrium, I mean, these relations should be broken when you anticipate. Then you will break down the data balance, so it should be the data balance.
Why do you think that it is going to be broken with dissipation?
Oh, because the data balance is going to have dissipation. You won't have dissipation when you break down the data balance. Otherwise, you won't.
Okay.
It's just, I mean, it's an active proposition of physics. Classic proposition of physics.
Okay.
And this is, I mean, Hubble's theorem or fluctuation dissipation theorem in general.
So there is no questions.
I have a question. So you have some dissipation in those harmonic potentials.
Yes.
So the ions lose energy, right?
Yes.
But does this also contribute to the heat of the bath, or not?
The dissipation contributes to
So it's the heat of the energy that is lost converted into
yes.
Yes.
It's like
Okay.
yes, as much energy. I mean, the energy that the device is throwing to the cold bath is going to be proportional to the dissipation coefficient of this bath. Or not? Yes. If
So all the energy that is dissipated will go to the other bath, or will some of it also stay in the bath?
can you repeat the question?
So the energy you dissipate, for example, in the hot bath,
Yes.
will go to the cold one? Or
No.
Okay.
It's like we have one ion here, and this ion is dissipated and at the same time acted by some forces. So and here the same. At the same time, this ion is affected by the other ion. So, for example, if the ion that is here is going to be more excited because the random forces are going to be bigger, so it's going to, like, what I understand is that this energy is going to be given also to this ion, and this ion that is moving, affected by the other ion and by the random forces, is going to dissipate this energy by the dissipation coefficient of this path.
But when both at the same temperature, will they both not move, or will they move together? Or?
Yes, they are going to move, and yes, and both are going to have like similar energy and are going to dissipate the same in each path.
They are then not stamped oscillators, or are they? I thought this dissipation coefficient is like the stamping coefficient.
They are, I think they are not that.
Okay. Yeah.
Yes.
Makes sense.
Can you go to the plot of the things?
This one.
Because I can see what you are representing in the y-axis. It's too small.
Okay, I have the spectral density multiplied by the masses of each ion.
And you have several lines here, but you have not.
Okay.
So very. And also you have to color, but they only one. Yeah.
Okay, yes, here maybe you cannot see it, but there are two lines.
One dash, one.
Yes, one blue dashed line, that is like this one, and a solid black line, that is like this one, and is the spectral density of one ion, and the other is the spectral density of the other ion. And these vertical lines are given by,
the poles.
yes, by the poles, yes. Yes. And the x-axis, the frequency.
You did one something before about one of the poles is the last one, you see what then. They do have one of the beats. One of the beats. It's very deep.
Okay, we know that the imaginary part of, we know that each pair of poles produce a peak, and the position of the peak is given by the imaginary part, and the real part is associated with the decay of this mode, and the real part is, if we have a dissipating mode, the width is going to be bigger, and that's why we cannot see here this really broad peak that should be like here. We should be here a small peak, and here a small peak of the spectral densities.
This solid line looks like it's suppressed. An anti-peak, let's say.
Here.
So I still don't get the proof in this.
I mean, we should expect a peak here.
Why
Sorry?
In which one should we expect the peak?
In both spectral densities.
But they have the same real value, so they should be in the same position. The peak should be in the same position.
Yes. I don't get your question.
So if you go to the plot of the poles, four poles, they have the same region. This from here, they have the same arm here.
This one?
Yeah.
Yes. This one is not here. It's just a bit on the other side. So. Okay, yes.
So maybe, so what we see the values, I think the values of A, which is a dynamic matrix. What?
Just yes. I should explain this
And,
more. This is
okay.
the equation of motions of the two-ion system.
Yeah, okay.
And yes, and the random forces are here, and this is the other part.
So the random forces come from the thermal path.
Yes, yes,
And there's some little nudges.
yes.
Maybe, so we have an intuition to understand why the spectral density has an impact on the flux. So it's something like they need to be matched to like resonate and transfer energy.
Yes,
like that. That's
yes.
the idea.
I think it's like in do you know the Oppenheimer approximation or something like that? Like when you have electrons, well, it's like it's what you said, essentially what you said, that we need a kind of yes, similar frequencies in order to one system to be affected by the other.
One of the Nquire is an analytic information,
Is that
same as the secret wall or the other one, or video information, everything is the same thing.
okay?
What you are doing is that you can solve ball dynamics somehow in an independent way.
Yes.
For instance, in ball dynamics, the electrons move much faster than
That the nucleus.
nucleus, and then you can solve the quantum dynamics.
Yes. You suppose that the electrons do not affect the dynamics of the nucleus.
They affect that.
They are
it's an infield.
Okay.
Maybe they break over if you are integrating over a long time, it makes some kind of infield approximation. And then you can consider the effect as an infield. And then the other way around, you solve the A gradient. But it doesn't mean that it's not affected.
Okay.
So here, why here you are saying that when you have different time scales in both systems, they behave as an isolator, they have similar time scales, they behave as a secondary.
Okay. Yes. Well, first of all, it was used. So
No, but look at the physical intuition, your physical intuition.
my physical intuition is like we suppose one it's like when if we suppose one ion is oscillating slowly and we suppose another ion with a high frequency and both of them are coupled. When this ion is moving, this is my intuition, I don't know. Maybe this ion is going to like have a full oscillation, so it's the force act over the slow ion is going to have first one sign when it's like getting close and the other sign when it's getting far. So it is going to be average in some sense. So the slow ion is not going to be affected.
But I think in this picture, in your picture, the natural time scale is not given by that. It's given by the spring in the middle.
Sorry?
The spring. The interaction between the
Do you think-
atoms is given with the model by spring.
Yes, I'm okay.
With kappa, with k, this
Yes.
is the time scale interaction because you are talking about the interaction between one ion and the other. So and that's the is mediated by this split.
Yes,
So the point is that if one is oscillating very fast, not with respect to the other time, but with respect to the time scale given by the spin, like the kappa, the frequency of the kappa, then essentially one can move, but the energy is not transferred to the other side.
okay.
But it doesn't matter how the other is moving. It's the time scale, it's not the time scale between ions, the time scale between each ion and the kappa, the table. So,
Okay.
I guess.
But then where's the asymmetric for the tension?
This is the next, it will be the next question, but
Okay, I get your point, and I am not sure about it. I have to think about that, but I think it's important not to compare both with kappa, but between them, but I'm not sure.
So this means that at the end, the only thing that matters is the frequencies of each system and not anything in the between them. So you don't need to have any specific material or anything between the two paths to have this asymmetry, right?
Yes, it doesn't matter. Well, what it was said is it doesn't matter how you couple both things. What matters is, yes, the frequencies. But we only check for harmonic coupling.